Have you ever just looked at a globe and wondered how that perfectly spherical shape is somehow translated onto the totally flat pages of a world atlas? Or, maybe you've tried to flatten out an orange peel and noticed how it inevitably just tears and stretches everywhere? So how does a mathematician actually map a curved, three-dimensional world onto a flat piece of paper without losing the essential truth of its shape? Well, welcome to This Explainer. Today, we're going to explore the mathematical foundations of that exact problem. We are diving deep into the cartography of the abstract. Specifically, we're looking at how mathematicians rigorously define, map, and measure the very concept of a surface in 3 dimensions. Trust me, by the end of this explainer, you're going to see the shapes around you not just as everyday objects, but as beautifully complex, completely chartable mathematical landscapes. So here's our roadmap for a day. First, defining a 3D surface. Second, patches and atlases. Third, the tangent space. Fourth, navigating orientability. And finally, measuring the surface. Let's get to it. Part 1, defining a 3D surface. Zooming in on reality. Okay, let's dive right into this. To really understand surfaces, we first need to completely flip our perspective. We have to stop looking at the whole object at once and start zooming in. Think about this for a second. The surface of the Earth, although actually nearly spherical, appears to be a flat plane to an observer who sees only to the horizon. I mean, when you step outside, you don't literally feel the curvature of the Earth, do you? You just feel the flat ground under your feet. This illusion of flatness at a superlocal level, that is the absolute core of differential geometry. So the crucial point is how we actually formalize that intuition. Mathematically speaking, a surface is defined as a subset of 3D space that looks exactly like a piece of flat 2D space in the vicinity of any given point. Basically, if you pick a spot on the surface and zoom in close enough, that tiny neighborhood absolutely must behave exactly like a standard flat XY plane. If it doesn't, well, then it's simply not a surface. And this idea brilliantly illustrates just how strict that definition really is. Take a cylinder, for example. No matter where you zoom in on a cylinder, even right on its curved wall, if you look close enough, it maps perfectly to a flat plane. It easily passes the test. But now, think about a cone. If you zoom in on its smooth sides, yeah, it's totally fine. But what if you zoom in on that sharp vertex right at the very tip? It will literally never look flat, no matter how ridiculously close you get. Because of that one sharp point, a complete cone is technically not a surface. To make it a true mathematical surface, we actually have to go in and remove its sharp tip completely. Crazy, right? Moving on to part 2, patches and atlases. The mapmaker's tools. Now that we actually know what a surface is, something that is locally flat, how do we go about mapping it? Well, we need the right tools. Enter the surface patch. A surface patch is a continuous mapping, what the math folks call a homeomorphism, between a flat 2D set of coordinates and a very specific region of our 3D surface. Think of a surface patch exactly like a single page in a city street guide. It just represents a small, manageable chunk of a much larger, complicated world projected onto a flat page so we can actually sit down and do calculations on it. But come on, a single page rarely covers the whole city, right? And a single flat map certainly can't cover a whole sphere without tearing or overlapping somewhere. That brings us to the atlas. An atlas is just a collection of these surface patches that, when you combine them, seamlessly cover the entire surface without missing a single spot. Just like mapping the globe requires multiple flat maps to avoid massive distortion up at the poles, complex 3D surfaces mathematically require a full atlas of multiple patches. However, you can't just slap any random map onto a shape and call it a day. For a surface patch to be considered mathematically regular, it has to pass a pretty strict calculus checklist. Step 1. The mapping must be infinitely smooth. This means we need to be able to take its derivative over and over and over again without ever hitting any sharp, jagged, mathematically undefined corners. Step 2. The directional vectors on that surface must be linearly independent. This basically just means the grid lines of our map can't collapse into a single line. And that makes sense, right? If your grid lines collapse into one line, your map is basically useless. You can't navigate a city in only one direction. The lines have to actually spread out and define a real two-dimensional area. Which brings us to part 3, the tangent space, standing on the surface. So, we've built our maps, but what does it actually mean to stand at a specific coordinate on that map? Imagine you're standing on a hilly landscape. If you were to drop a perfectly flat sheet of glass so that it just barely kisses the ground exactly at your feet, you've just visualized the tangent plane. But mathematically, we construct this by looking at smooth curves that travel right along the surface, passing exactly through your spot. If we take the derivatives, meaning the exact velocity and direction of all those curves right as they zip past your feet, those velocity vectors span outwards to create a perfectly flat plane that brushes right up against the 3D surface. And once we have that perfectly flat glass plane at our feet, we can define a totally critical signpost, the standard unit normal. By calculating the cross product of our surface vectors, we generate a brand new vector that points straight up and away from our localized flat map, perfectly perpendicular to the surface. It is the absolute mathematical definition of up for that specific point on the surface. All right, part 4, navigating orientability, choosing a side. Now that whole concept of up actually introduces some truly bizarre 3D properties. Which brings us to orientability. For a surface to be considered orientable, it has to follow some strict rules. Chief among them, it must allow for a consistent unit normal vector everywhere. This means the entire surface has a universally agreed upon inside and outside, a distinct positive side and negative side. Because we can agree on which way is up everywhere, we can look down at our tangent plane and consistently define exactly what an anti-clockwise rotation looks like across the entire shape. But you know, differential geometry doesn't just study the nice, well-behaved shapes. I want you to challenge yourself for a second to visualize something that is totally impossible in our standard daily lives. What happens if you walk along a continuous loop on a surface, keeping your head pointing straight up the entire time? But when you return to your exact starting point, you find you are hanging completely upside down. On a surface like this, the very rules of up and down completely break. Enter the Mobius band. It is the absolute ultimate mathematical rebel that perfectly illustrates this phenomenon. If you trace a normal vector around a Mobius band, when it finally comes back to the start, it's suddenly pointing in the exact opposite direction. A continuous unit normal is literally impossible here. Therefore, the Mobius band is a non-orientable surface. It literally does not have two distinct sides, it only has one. It's wild. Our mapping tools start to reveal geometries that completely defy common sense. Finally, part 5, measuring the surface, the bug's perspective. We've defined surfaces, mapped them with atlases, built tangent planes, and figured out if they even have two sides or just one. Now, how do we actually apply all these tools to measure things in our 3D world? I want you to imagine a stark contrast between a 3D observer and a bug. An observer, just floating in space, measures the distance between 2 points on a curved surface by just drawing a straight line, cutting right through the empty space between them. But a bug trapped on the surface, it can't fly through the air. To measure distance, that bug must walk along a curved path that is completely glued to the geometry of the surface. Their measurements of the exact same 2 points are going to be totally different. We need a tool that does the math purely from the bug's perspective. And this is where the first fundamental form comes in. Think of it as the ultimate mathematical translation device. It's a geometric object that takes the coordinates from our flat 2D patches and uses them to calculate the true lengths, angles, and areas, precisely from the bug's perspective, accounting for absolutely every curve and dip in the 3D geometry. So the really crucial takeaway here is the sheer power of the first fundamental form. It computes the actual lengths of those curved surface paths the bug has to walk. It determines the true angles between tangent vectors, and arguably its greatest mathematical superpower, it is entirely immune to reparameterization. It literally doesn't matter if you draw your map's grid lines horizontally, vertically, or completely diagonally. The first fundamental form grounds all this abstract calculus into tangible, consistent map making. The true geometry remains completely unchanged, regardless of how we choose to draw our map. Which leaves us with a truly fascinating, provocative thought to wrap up this explainer. We started all of this by saying a surface is just something that looks perfectly flat when you zoom in on it. But if every surface looks flat up close, how does the bug, who can only see things up close, ever actually know it's walking on a sphere instead of a flat plane? How do we mathematically measure true underlying curvature entirely from the inside? Well, that question unlocks an entirely deeper level of geometry, and it's something I highly encourage you to ponder. Thanks so much for joining me on this mathematical journey. Keep zooming in, and I'll catch you on the next explainer.